This is a video I've been wanting to make for quite a while because honestly I had no idea what the results were going to be. Ever wonder exactly what these little rubber flaps inside your shocks do? Well, they do quite a bit and we'll dive deeper than anyone else. Of course, there will be theory, math, and real examples. This is the definitive guide to flexible membrane IFPs, also known as shock bladders. On this channel, we suss out the science behind our grown-up toys. There are two kinds of shocks in RC, emulsion and bladder, and they are completely different. We will only be talking about shocks with an internal rubber bladder in this video. Since this is mostly a crawler channel, we're going to focus on 10mm diameter shocks such as the Deluxe DraftTech and Traxxas Big Bore. 10th scale buggies and truggies generally use 13mm shocks, and on 8th scale you'll see 16mm. The concepts here will translate to any size bladder shock. Here is the basic design of a high-performance full-scale shock. This is the piston shaft that's connected to the axle or suspension arms and moves up and down. This is the piston head, which moves through the oil and creates damping force resistance. This is the internal floating piston, or IFP. It's actually more like a piston head because there's no piston shaft attached to it. This piston head floats back and forth and keeps the oil from mixing with the air on the other side. This is the air chamber, which is pressurized, and it's usually pressurized with nitrogen. So why nitrogen? It supposedly seals better than air because the molecules are bigger. However, the Earth's atmosphere is already 78% nitrogen, so I'm a little skeptical. More importantly, it's an inert gas, which means it's more stable over a wide range of temperatures. It also won't explode, and it isn't corrosive to the internal components of your shocks. Your RC car, however, is just going to have normal air, and that's just fine. This IFP does a couple of things. First, it pressurizes the oil to the same pressure as the reservoir. This reduces cavitation, which is when bubbles form in the oil under fast shaft movement. It also compensates for thermal expansion in the oil, or really any of the components that might change size when they heat up. One of the biggest things that it does is compensates for the oil displacement when the piston enters the oil. And finally, it also adds some degree of spring rate to the piston, which may or may not be desirable. But how much does it really add? On a scale RC shock, this complicated floating piston is simplified with a flexible membrane, a rubber bladder with non-pressurized air behind it, instead of charged nitrogen. This bladder is expected to do all the same things, thermal and volume compensation, but it's not pressurized, so its effectiveness against cavitation is unknown, and we're going to try to find out. First, let's look at some theory and math. According to Boyle's law, pressure is inversely proportional to volume. That just means as the volume goes up, the pressure goes down. It also means that if you change volume, the pressure changes, and vice versa. Let's assume this has a pressure of 100 psi and a volume of 100 cubic millimeters. Now we shrink the container, so the container is now half the size, only 50 cubic millimeters. What happens to the pressure? It doubles. So when you cut the volume in half, the pressure doubles. Pretty straightforward. This is important to a bladder shock because as the piston moves into the oil, the piston shaft takes up space in the oil and causes the oil side to increase in volume. This compresses the bladder and reduces the volume of the air chamber. When that volume goes down, its pressure has to go up. But does it change enough to make a difference? As the volume goes down, the pressure goes up. Let's take a look at what that does on a shock. We're going to test some bladder shocks. Now this is a deluxe short shock. There's lots of shocks that share the same design and architecture. And in the top is this bladder. And this bladder does a few things. What we're going to find out is, does it affect the tuning at all? So the bladder sits in the top, and I've got two different ones here. The deluxe ones seem to be a stiffer material, and they're a little bit thicker than the Traxxas ones. So we're going to test both and see what kind of difference, if anything, they make. So the way the bladder works is it sits on the top, and then I've machined out this top cap so that we can see what the bladder does when we push on the piston. But of course we need oil first. Now, one thing that's interesting is this sits down inside. It's down into the oil area of the shock. And this is a short deluxe shock, which has, they say, 23 millimeters worth of travel. Let's double check that. So I've got a nut on here that's just a placeholder. And this placeholder is, at the end of the threads where your rod end should be. And I'm getting 24 millimeters, plus there's a little bit more travel down into here. So Deluxe says 23. This is probably 24.5 millimeters of stroke. So let's take a look at this. When the piston is compressed all the way, you can see it pokes out the top. And that's obviously going to hit the bladder. Unless the bladder moves out of the way. So let's fill the shock with oil. I'm going to use 10 weight just because I really don't want to have the effect of the oil influence anything, but I do have to have it filled up with oil to conduct the experiment. Oils and fluids are generally considered incompressible. There may be some microscopic air bubbles in this, so I'm going to use my beloved Tamiya shock pump to draw out any air that might be in the oil. Oh, there's some bubbles coming to the top. Look at that. Those air bubbles in the oil will make the oil slightly compressible, which we don't really want for this experiment, and you don't really want in real life either. So this Tamiya vacuum pump is one of my favorite tools, and I will put links to all the tools you see in this video in the description, and anytime you shop with those links, it supports the channels and allows me to do even more videos like this one. So I let it sit for about no more than 2 minutes. Now we've got all the air removed. And I have this filled completely to the top. I'm going to drop this in. It's going to overflow everywhere, which is fine. You want to push it into place. We're going to clean this up later. The important thing is that we get no air behind the bladder. So I'm going to push on the lid. Don't over tighten it. The piston is fully extended, and now let's see what that looks like. Look how much that bladder moves when the piston comes in. So we were wondering if the piston would crash into the bladder. I'm going to say that bladder stretches out of the way enough that it doesn't hit. Plus, it doesn't feel like it's hitting anything. So the first thing we want to do is evaluate any spring rate influence from the bladder. You can see there's a very small amount of spring rate pushing on the piston. So that may or may not be spring rate that we want. Now you might be asking yourself, what's actually pushing the piston back? And you're probably thinking, well, it's just pushing on the piston head. But that's not exactly how pressure works. Let me show you something that might mess with your head. Now, I'm going to replace this piston with an identical piston, only without the piston head. So now we can tell whether or not the piston head is in charge of pushing that piston out. So I kept this circlip in place just to keep the piston from falling out altogether, but there's no piston head on this piston. Put on my travel stop, and there we go. We've got a sliding shaft, same travel, but no piston head. And I'm going to have to bleed that again. All right, so now we've got it reassembled, nicely bled, no air on the inside, bladder installed, see-through cap. Do you think this is going to move without the piston head on it? Sure does. It looks like it moves the same amount as the piston head version, only without the piston head. This is why. You need to understand how pressure acts inside a container. Let's start with a round container and say the blue arrows represent the air pressure on the inside. The internal pressure creates forces that push against the wall of the container. These forces always act normal to the surface. Normal is just an engineering word for perpendicular or 90 degrees. Whether the surface is flat or curved, the forces always push perpendicular to that surface. It also doesn't matter what shape the part is. The pressure is always normal to every surface and exerts the same force at every point on the surface, no matter what the shape is. Here is the shock once again. Let's add in all the forces from air pressure. The blue arrows are external atmospheric pressure, which is actually 14.7 psi. There's no such thing as zero pressure unless you are in space. The red arrows are the internal pressure of the oil. Let's assume the piston is sitting at its neutral happy spot when the oil pressure and bladder pressure are the same as the exterior pressure. We can start by removing the arrows pushing on the outside of the body because the shock body is rigid and immovable. We can also remove the arrows in this direction as well. We can also remove the arrows pushing sideways on the shock shaft because they don't do anything, they just cancel each other out. And on the inside of the shock, we can do the same. We'll remove any pressure that is pushing on the interior sides of the shock body because they are not moving the shock body. The forces are still there, they are just contained and constrained by the rigid walls. We can also remove the arrows pushing sideways on the shock shaft, same as we did on the outside. Now, here's where it starts to get interesting. The pressure in the oil is the same throughout all the oil. Remember that the forces from the oil pressure always act perpendicular to any faces in contact with the pressure. In this case, in contact with the oil. So there is pressure on both sides of the piston head, and they cancel each other out. These forces cannot cause the piston to move, so we can erase them. We might as well erase the piston head while we're at it. So this leaves only the pressure of the oil pushing on the very tip of the piston shaft, which is 3 millimeters in diameter. And it is reacted by the same area on the opposite end, on the outside of the shaft. Assume the blue pressure is 14.7 psi and the red pressure is something higher. This means the red force is greater and will push the piston shaft out. The piston head itself has no effect, so it can be removed, which is precisely what I did in the experiment. So now that we know how pressure acts on the inside, how much does that actually push on the shaft? Let's turn to a little more math. If you know the internal pressure, you can figure out how much force is pushing on a given surface area. Suppose you have 100 psi and you have a surface area of 10 square inches. If you multiply those together, the units of square inches cancel each other out, which just leaves force. 100 times 10 equals 1,000. That means if the internal pressure of 100 psi is pushing against a surface that is 10 square inches, it will push with 1,000 pounds of force on that surface. Jason Brockmeyer from Deluxe was nice enough to share his actual 3D CAD with me so I could get exact numbers for this research. All three versions of DravTech caps have the exact same volume inside. So we'll just look at one. So we've got the bladder installed, and this is the air volume behind that bladder. And I've made a model of both bladders. The orange DravTech and the black Traxxas. So what I did is I made a revolved feature that captures all the volume on the inside. And we'll simply measure that volume and use it for our calculations. "274 cubic millimeters. And I did the same thing with the Traxxas bladder. 344 cubic millimeters. Quite a bit bigger. Let me start by measuring the spring rate coming from just the bladder without the effect of the air pressure behind it. So now let's attempt to measure what spring force this bladder is adding to the system. You may have seen this setup in my spring rate video. This is a really great force gauge I got on Amazon. And what I'm going to do is attach the shock loosely. And what we're going to do is just measure what the force is. The shock moves 24 millimeters. I'm just going to move it a solid 20 millimeters and see what that force is. So we're starting with 0. So I'm just going to put some spacers. There's a little bit of play here. I'm going to call that 0. And I'm going to 0 the unit. All right, and now I'm going to push it exactly 20 millimeters and take some readings. I'll probably do 5, 10, 15, and 20, see what happens. So the first measurement's going to be 5 millimeters. So I'll call that 13. I'm going to push it 10 millimeters. 18. Push it 15 millimeters. 25. And then 20 millimeters. $34. Now, to be most accurate, I'll repeat this multiple times off camera so I don't bore you, but you do really need to take multiple measurements in both directions to get as accurate of data as possible. Now I want to repeat the test with the thicker deluxe cap. Now what I'm going to do is replace this see-through cap with a closed cap, and that will trap some air behind the bladder. And that trapped air should act as an air spring. But does it add much to the system? Let's find out. So now we know how much spring force is coming from just the flex of the rubber bladder with no pressure behind it. Now let's add back the sealed air volume and measure what the combined spring rate is. But first, I bet we can predict what it should be with a little more math. So back to our shock. We know the piston is 3 millimeters in diameter. The formula for area is pi times the radius, which is half the diameter, radius squared. If we know the area of the shaft and the height of the shaft, we can multiply those together and get the volume. Pi r squared is the equation for the area times the height equals the volume. This will allow us to calculate how much oil is being displaced by the volume of the shaft. So the average number for the bladder only averaged 34 grams of force, and the calculated number based on 20 millimeters of displacement was 51 grams. So that equals a predicted force of 85 grams when we move 20 millimeters. Let's see what the gauge says. "85, 84, that's pretty close." Now, so we can construct the entire spring curve, I'm going to take the other readings as well. So now I'm going to plot those, and we'll see what they look like. So this one has the orange Dravtech seal. I bled it with a piston fully extended, vacuum pumped it, and it already looks like there's a lot more spring force added. The bladder alone contributes about 70 grams of force. And based on the compression of the air and the air spring produced by the reduction in volume, we should get about another 77 grams of force. So that should be about 150 grams of force at 20 millimeters. So let's see what we get with 20 millimeters of stroke. Yeah, based on these readings, it's about 138, 142. Looks like the math is correct. Now, I don't expect this to be linear. The rubber bladder, because of its shape and also its material, it's probably not a linear spring. Also, air volumes are generally not considered a linear spring. So I'm going to measure 4 points, and that'll let us know if it's a straight line or a curved line. Again, I will do several more measurements off camera so we get good data. Next, let's look at the full spring curves of each system and decide how it affects the overall spring rates. You can build a Dravtech shock with either a Traxxas 2362 Rebuild Kit, which Deluxe used up until about 2024, or the Deluxe Orange Bladder that they designed on their own. The orange one fits much better and is stiffer, and Matt Beast will sell you some if you want to upgrade your old shocks. Here are the average forces for the Traxxas Black Bladder. I measured at least 3 trials and averaged them at each of the different strokes. I suspected that the spring curve would be progressive, which means not a perfectly straight line. So I took 4 points to help define the curvature of the line. You can theoretically define a straight line with just 2 points. Here are the Traxxas numbers plotted. As I suspected, they make a curve. Across the bottom is shock stroke. On the vertical y-axis is the force pushing back on the shock shaft. The darker line is the bladder only, and the blue line is the bladder and the air cap combined. Here are the average measurements for Deluxe. You can see every plot has the same upward curvature, which we expected. Deluxe has higher forces. That makes sense because the bladder is a little bit lower profile, meaning it doesn't trap as much air, and it feels like it's a stiffer rubber. Again, the lower, darker one is the bladder only, and the yellow one is the bladder and the cap combined, the shock fully assembled. If you're really good with data collection and plots, you may be asking why these plots don't pass through zero, or why don't they all start at the same place. This is an indication of the difficulty of getting the bladder pushed in perfectly each time and getting a consistent 0 point, as well as the fact that there is different startup friction with each assembly. While this is not ideal, it's not critical because we are simply going to extract the slope of each of these lines, which will be the spring rate. Its 0 point is less important. For each plot, I added what's called a trend line. These lines are a mathematical best fit through the data. This data is really good because it makes a nice curve. It's not scrambled up and down, which means the fit quality is quite good. Just for reference, here's what an exponential trend looks like. It follows the curve much better, but this equation is much tougher to interpret. This gives us the instantaneous slope, which is a lot harder to visualize. So let's stick with a straight line because that gives us the spring rate at a glance. So since we're using the linear or straight trend line to approximate the data, the straight line gives us the average spring rate across the entire range. The spring rate number is a number we can compare directly to the spring rate of the coil spring in the system. And we will just use common sense judgment to remember that the bladder and air spring is a little bit softer at the beginning of the stroke and stiffer at the end. If you've watched my videos on spring rate, you know that spring rate is rise over run. Rise being the force and the run being the stroke. The force over stroke. For example, at 120, you have to subtract the y-intercept, 15.5, then divide by 18, and if you do that, you'll get a slope of 5.82, which is the spring rate in grams of force per millimeter, grams per millimeter. And you may remember this from middle school. And here you thought you'd never use that math. Okay, if you're still with me, we're about to learn what this all means on our rigs. RC car shocks are amazing. We've seen that a simple bladder shock actually employs 3 different technologies: steel coil springs, rubber or elastomer elements, and an air spring. There are full-size vehicles who go to great lengths to combine coil springs with air assist springs and rubber jounce bumpers in order to tune in the exact response they want. And it makes sense. Each approach provides a different response, and we can leverage each of those for RC tuning. In this video, we are only talking about the spring curve response. You still have the oil damping curve and shock mounting angle options as tuning parameters, and I've produced several videos on those topics. So for all bladder shocks, here's what we know. Yes, the bladder alone does add a small amount of spring rate. Yes, the trapped air behind the bladder can add a lot of spring rate. If you are running heavier springs, then the added spring rate may not be a big enough percentage to matter. If you are running ultralight springs or no springs, which may be the case with a crawler, then it could be enough to influence that spring rate noticeably. If you're running a very short stroke shock, then there probably isn't enough volume displacement to build up significant pressure to make a difference. If you're running long stroke shocks, then the air pressure can be quite high from the shaft displacement. A couple things to keep in mind. I measured these shocks immediately after I capped them. The pressure is at its highest and will only go down over time. This is especially true if you're running deep droop and store your rig compressed. You are storing it at max pressure, and even the best shocks will lose pressure. So I recommend to store your vehicles on blocks so the shock is not pressurized and so you don't get flat spots in your tires or inserts. Also, many caps may not be designed to hold air long term, so if you've got a bolt running through the top of your cap, You might add some RTV or pipe dope to make it more airtight. Temperature compensation. Small RC shocks don't dissipate enough energy to get hot, particularly not a crawler. So thermal compensation is not really a concern. However, if you change altitudes or drive in extreme temperatures, the Bladder has you covered. Cavitation. We see that there can be a significant amount of pressure building behind the Bladder. Cavitation will happen when the shaft speed is at its fastest, which is generally about mid-stroke, and that is where the pressure is about half the potential maximum that I estimated. I am seeing pressures from as little as 3 psi up to about 30 psi at the mid-stroke point. I don't think I can predict exactly at what point cavitation will occur, so I will have to build a clear shock body so we can see visually inside. 20 to 30 psi seems like a pretty good amount of pressure for such a tiny shock, but we'll have to save that study for another time. Now let's talk specifically about 10mm crawler shocks. This is not a paid promotion, just the facts. Everything you see in my videos, I paid for myself. I like deluxe shocks because they have so many options for custom builders. 4 body lengths, 2 bladder options, 9 piston lengths, 4 piston heads, and 10 different rod end configurations. And they will sell you whatever individual parts you want. The Traxxas Big Bore 2660 is a similar design, but it only comes in boring brown, but it has many parts that are cross-compatible. So here is the spring rate we get for the black Traxxas Bladder, and the spring rate we get for the deluxe orange Bladder. And 7.1 is the spring rate of an ultra soft spring. Remember that this is an average linear spring rate, and the actual spring rate is actually curved. Softer at the beginning, stiffer at the rear. This is important because if you're running full droop or very high droop, 80 to 90% compression, then you want to be sure and look at the end of this curve. This is where your vehicle lives, and because the spring rate is progressive, it is stiffer than this average number at the end of the stroke. An ultra soft spring has a rate of 7.1 grams per millimeter. The Traxxas Bladder adds about 50% more to that, 3.6. The deluxe spring rate doesn't quite double your spring rate, but it's about 90% more when you add the fudge factor of it being steeper at the end than the actual 5.8. Here are my calculations for each of the available deluxe shock lengths with both Traxxas and deluxe bladders. You might want to screenshot this so you know what forces you might be dealing with from each of these columns. I've also listed the PSI that's trapped behind the Bladder upon full compression. This long shock says it's 59 PSI. That seems like a lot, so based on our calculations, if there truly is 59 PSI behind the Bladder at full compression, 31 millimeters, we should see around 360 grams of force on the piston shaft. Let's go check that out and see if it's right. So we've got a long shock here. It's been bled and vacuum pumped. It has 31 millimeters of potential stroke, and we're looking for about 360 grams of force at 31 millimeters. So I'll start by giving it 20 millimeters. Now I'll give it 30 millimeters. And at 30 millimeters, we're looking at about 200 grams. Let's add in one more to reach 31. And that overloaded the device. That means it's over 400. So this does make sense. Because of the progressive and exponential nature, the force ramps up faster and faster. So here we are at 30 millimeters, and we've only got 175 grams, and that extra one more millimeter really ramps it up fast, pushes it over the top, and it's over 570. So that just shows the nature of how steep it ramps up later in the stroke. This long shock is actually behaving exactly as expected. Our estimation was based on a purely linear assumption, If it were purely a linear spring response, it would be 360 grams of force at 31 millimeters. But since it's progressive and exponential, the curve starts to rise very steep at this end. This is what it would look like if we could continue traveling. And that's exactly what we were seeing. Right between 30 and 31 millimeters, it really ramps up quickly. You can see it pulling away fast from our projected number. Remember, there's no piston head on the end of these pistons. The pressure is pushing only on this small area on the end. So now, here are the results you've all been waiting for. On the left is each of the different shock lengths with both bladders, because we know the bladders make a difference. Across the top, you have the 4 most common spring rates available from Low C and Deluxe for 10 millimeter shocks. And what I've done here is put the percentage of spring rate coming from the bladder compared to the spring. So if you see 100%, that means the spring rate is doubled with the addition of the bladder and the air spring. Let that soak in. If that doesn't make sense, here is another way to look at it. Suppose you combine the bladder and the spring rate, you get this multiplier of the spring. So if your spring is 1 and you add an extra short plus a Traxxas bladder to it, you're going to get 1.6 times whatever the spring rate alone is. For example, an extra soft spring with an extra short shock and a deluxe bladder is going to give you over double what the spring alone produces. Alternatively, if you look at a long shock with a softer Traxxas bladder and combine that with a stiff spring, then it's barely 1.1 times what the spring alone is. It's basically 10% more. Here is one last way to look at it. It's color-coded. Red means the bladder and shock length have a huge effect on the spring rate. Yellow means it has a moderate effect. Green means it has a low effect. If it's white, there's almost no influence. You're basically looking at just the spring rate if you're in one of these white blocks. So there you have it. Here is an opportunity for the industry. I'd like to see more bladders offered in different geometries and with different durometers. Also, how about some different sized air caps for different length shocks as an additional tuning option? In part 2, we will discuss additional strategies to tune the effect of the bladder. Most commonly, you can set the piston depth partway compressed when bleeding and capping. You could also port the cap so pressure doesn't build up and tune the volume. I'll show you the exact effect of these tuning options in the next video. Don't forget to like, subscribe, and turn on notifications. That way you'll be the first to know when that video drops.